Acceleration. Acceleration can be defined as the change in velocity over time. Now, this is oftentimes referred to as average acceleration. If you ever have a changing acceleration, then the average acceleration is going to be the total change in velocity over time. Oftentimes in class we're not going to be talking about changing accelerations, so this will be the same as our instantaneous acceleration, which can be found by using the slope of a velocity versus time graph. So the slope of velocity versus time graph gives us acceleration. Acceleration is a vector. This means that it has a direction. Now, we haven't talked much about vectors and scalars yet, but vectors are measurements that have to have a direction. Scalars are measurements that don't have a direction, much like mass or temperature. Those things don't need a direction, but velocity and acceleration all have directions. There are three ways to accelerate. You can speed up, slow down, and change direction. In the next two units, we're going to be talking more so about speeding up and slowing down. And when we get to centripetal acceleration, we'll talk more about changing direction. But essentially, since acceleration is a vector, that means velocity, changing velocity, will cause a change and produce an acceleration. So the amount of velocity, speeding up or slowing down, so that's changing it, increasing it from 3 to 4 meters per second, or from 3 down to 2 meters per second, that's speeding up and slowing down. But since velocity has a direction, then changing the direction, even though the 3 meters per second doesn't change, so if we go from 3 meters per second west to 3 meters per second south, that is an acceleration also because we changed the direction. So what does it mean to have an acceleration of 2 meters per second squared? Well, another way of thinking about 2 meters per second squared is 2 meters per second. And since acceleration is change in velocity over time, then that means 2 meters per second is that you are changing your velocity by 2 meters per second every second. Now that's positive 2 meters per second. We would think this means that it's speeding up, but that's not necessarily true. If we have an initial velocity that is negative 4 meters per second, then a positive 2 meters per second squared means it's going to increase in the positive direction. So negative 4, 1 second later, would become negative 2. And then a second after that would become 0. And then after that, it would start speeding up. It would go to 2, and then 4, and then 6 every second after that. We have our basic equation for acceleration equals change in velocity over time. Now, change in anything means final minus initial. So final velocity minus initial velocity divided by time is going to be equal to acceleration. We're going to rearrange this equation. We're going to multiply both sides by time. That cancels time on the right side, and that leaves us with final velocity minus initial velocity equals acceleration times time. Then we add initial velocity to both sides. We get final velocity is going to be equal to acceleration times time plus the initial velocity. Now this equation right here looks a lot like a linear function, and in the labs that we did, we got a linear graph on the velocity versus time graph because acceleration was constant, which means the slope was constant. And this looks a lot like a y equals mx plus b format. So with acceleration, what if we have a positive acceleration with a positive velocity? Well, this should be pretty obvious whether we speed up or slow down. Positive acceleration, positive velocity, we're going to speed up. But what about a negative acceleration with with a positive velocity? Negative acceleration with a positive velocity, well, that means we slow down, and that should be pretty obvious. Where it gets a little tricky is when we start talking about positive acceleration with a negative velocity. Positive acceleration with a negative velocity, we're actually going to slow down. And with a negative acceleration and a negative velocity, we actually speed up. Now, why is this? Why is it that we have a negative acceleration but we're speeding up? Well, consider this. Whenever we define positive and negative, there's nothing in nature that says negative has to be a certain direction. So you and another person can disagree on what direction's positive and what direction's negative. So let's say you say to the right is positive. Well, you see something moving to the right and accelerating to the right. That means a positive velocity with a positive acceleration. That means you see it speed up. Now, what if the other person says, no, I want to make to the right negative? Well, they're going to see a negative velocity and a negative acceleration, which means they should observe the exact same thing you did regardless of how you define positive and negative. So they should see it speed up also. Well, that's the same with the positive acceleration and negative velocity, or a negative acceleration and a positive velocity. Essentially, all you need to remember is that if your acceleration and velocity are in the same direction, it'll always speed up. If your acceleration and velocity are in opposite directions, it'll always slow down. For this reason, that's why I have a hard time using the word deceleration, because oftentimes when we hear the word deceleration, we think negative acceleration, which is not true, because you can have a negative acceleration and still speed up. Deceleration is technically slowing down. Slowing down is deceleration. So if you have your acceleration and velocity in opposite directions, then you'll slow down. If they are in the same direction, then they'll speed up. So with acceleration and velocity in opposite directions, that's when you're going to get a deceleration. Comparing graphs. So here we have a position versus time graph of an object that's moving a certain position given the amount of time. We also have a velocity versus time graph for the same object that's moving, so they both describe the same motion. Additionally, we have an acceleration versus time graph. So I want to analyze the position versus time graph, and I want to determine the slope at 2 seconds. Now, why do I determine the slope at 2 seconds? Well, for a position versus time graph, if you remember, the slope at any given point is going to be velocity. Now, it's hard to get a slope of a curve because it is not a straight line. So what we do is we take a tangent line at 2 seconds that goes through that point right there. Now notice this tangent line comes through, touches at just one point, and then comes off. So it doesn't cross the line at all, but it comes through and touches that one point and moves away. So let's get the slope of this line. In order to do that, we need to get 2 points. We get this point down here, which has a, you can see that it has a position of 7 meters. This point up here has a position of 23 meters. The 7 meters is at 1 second, the 23 meters is at 3 seconds. So let's get a slope of these 2 points. The slope is going to be change in position over time, or rise over run. We get 23 minus 7 divided by 3 minus 1. That gives us 16 over 2, so we get 8 meters per second. Now with that being said, if we go to the position or the velocity versus time graph at 2 seconds, we should get 8 meters per second. You can see here on the velocity versus time graph that at 2 seconds it indeed does equal 8 meters per second. So the slope at any given point on a position versus time graph is going to be equal to the velocity. Now let's take the area from 1 second over to 3 seconds. Now we haven't really talked much about area and what that means. We've talked a lot about slopes but not area. So this area right here is a trapezoid. We're going to actually split this into 2 sections. I don't really remember the area of a trapezoid, but I do remember the area of a triangle and a rectangle. So the area of a triangle is 1/2 base times height. Alright, so 1/2 the base times the height. In order to get the height, I can see the base, it's from 1 to 3 seconds, but the height I kind of have to gauge that. That's 6.5 meters per second here and 9.5 meters per second at the top. So 1/2 the base, it's 3 minus 1, and then the height is 9.5 minus 6.5. So it's half of 2 seconds times 3 meters per second, and that gives me 3 meters for the area of this portion right here. Now the rectangle at the bottom is just base times height. Well, again, the base is 3 minus 1, and the height goes from 0 to 6.5. So 2 times 6.5, and that gives us a total of 13 meters. Now if we take those and we add those together, we get 3 plus 13, and that gives us a total of 16 meters. Now what does this describe? Well, this area right here describes the displacement of the object between 1 and 3 seconds. If we look at the position versus time graph, we go up to 1 second and to 3 seconds. We see that at 1 second the position is 8 meters. At 3 seconds the position is 24 meters. Take the difference between the two and we get 16 meters, which was the position or the displacement we got from the previous part, from using the velocity versus time graph. So for the velocity versus time graph, if we take the area, we get displacement. For the position versus time graph, if we take the slope, we get velocity. So it's a lot of information. Let's go ahead and organize it inside of a chart. Position versus time graph, the slope, what is that going to give you? You should give you the velocity at any given point, which we call instantaneous velocity. The y-intercept is going to be the position when time equals 0. We call that initial position. The area of a position versus time graph, it doesn't give you anything. There's no real physical relevance to that. What about the slope of a velocity versus time graph? Well, if you notice the position versus time graph, the slope gives you instantaneous velocity. Hopefully you can see a pattern forming from this. From a velocity versus time graph, the slope will give you instantaneous acceleration. Now again, we're not going to be talking about acceleration that's changing, so instantaneous acceleration will be equal to the constant acceleration that we get from a graph. But if you do have a changing acceleration, then the slope of a velocity versus time graph will just give you the acceleration at that moment in time. The y-intercept for a velocity versus time graph, that's the velocity at the first, or at 0 time, which is going to be your initial velocity. Now the area we just talked about, the area of a velocity versus time graph is displacement, but I'm going to call it change in position. Now change in position and displacement are the same thing, but hopefully you can see the pattern that's forming from taking the area of a velocity versus time graph. Alright, so the slope of an acceleration versus time graph, well, that's a term we call jerk, instantaneous jerk. And if you have a changing acceleration for some reason, or a jerk that's increasing or decreasing, then that's just a jerk at that moment. The y-intercept for an acceleration versus time graph, if for some reason we do have a changing acceleration, is going to be the acceleration at 0 time, which we call initial acceleration. The area of an acceleration versus time graph we haven't really talked about, but hopefully the pattern is showing up. For a position versus time graph, the slope is velocity. For a velocity versus time graph, the slope is acceleration. For acceleration versus time graph, the slope is jerk. Now for a velocity versus time graph, the area is change in position. Now that goes back up to this graph, and hopefully the pattern you see with an acceleration versus time graph, the area is going to be change in velocity. So the slope of any graph goes to the next graph. We call that a derivative. A slope at any given point is called a derivative, and we're going to use those terms interchangeably, a slope and a derivative. The area at any given point, or for a range, actually you need a range for an area, the area is called an integral. Now an integral and a derivative are inverses of each other. And you can see that with this graph. Velocity versus time graph, if you take the slope, it's acceleration. If you take the area of an acceleration versus time graph, it's change in velocity. So you can see this kind of back and forth that goes from taking the derivative of velocity versus time graph, getting acceleration, and then taking the integral of acceleration versus time graph and getting change in velocity. Now this equation is going to be one of the equations that we use for accelerated motion. Now oftentimes I like to show students where these equations come from, not just hand it to you all and just expect you to be able to know. So we start with these two equations, these basic equations that we've already developed. Now if you notice from these equations, what they have that this equation up here does not is both of these equations have time in them. So what we're going to do is we're going to take this equation right here and we're going to isolate time. So we subtract initial velocity from both sides, and then we're going to divide both sides by acceleration. And that gives us that time is going to be equal to final velocity minus initial velocity divided by acceleration. Then we take that time and we plug it into the other equation wherever we see time. That gives us displacement is going to be equal to 1/2 times acceleration times final velocity minus initial velocity over acceleration, this part right here, which was time, and that's going to be squared, plus the initial velocity times, again, time, which is final velocity minus initial velocity over acceleration. We're going to distribute the squared to the numerator and denominator. We're also going to distribute the initial velocity to the numerator of the other term. That gives us 1/2 times acceleration, and you get the final velocity minus initial velocity squared, and divided by acceleration squared, plus final velocity times initial velocity minus initial velocity squared. That's both of these terms with being multiplied by initial velocity divided by acceleration. Now this first term over here, you notice that acceleration actually cancels. Only one of the accelerations on the bottom cancels with the acceleration over here. We're also going to distribute the 2 into the denominator of this term. Also, we need to FOIL the numerator when we got final velocity minus initial velocity quantity squared. Alright, so let's do all this. So final velocity minus initial velocity squared gives me final velocity squared minus 2 times final velocity initial velocity plus the initial velocity squared. Now the 2 and the a are still on the bottom, and then we have this term over here which stays the same. Okay, using this equation, so we're going to multiply both sides by 2 times acceleration. Notice the acceleration is going to cancel from here off of the denominator, and then we're going to multiply both of these terms by 2. Well, notice the 2 is going to cancel from the numerator and the denominator here, but the 2 has to be distributed over here because there's no 2 to cancel. Alright, so we're left with 2 times acceleration times displacement is going to be equal to final velocity squared minus 2 times final velocity initial velocity plus the initial velocity squared. It's just the numerator of this part right here because the denominator was canceled. And then we got 2 times final velocity initial velocity minus 2 times initial velocity squared. Now notice that we have a negative 2 final velocity initial velocity and a positive 2 final velocity initial velocity, so those are going to cancel. We also have a positive initial velocity squared and a negative 2 initial velocity squared, so one of those are going to cancel. And that leaves us with 2 times acceleration times displacement equals final velocity squared minus initial velocity squared. So to rearrange this, we're going to add initial velocity squared to both sides. That cancels it from the right side, and that leaves us with our final equation where final velocity squared is going to be equal to initial velocity squared plus 2 times acceleration times displacement, which is our equation we were trying to get to.